This video will show my design for an ALU, or Arithmetic and Logic Unit, designed using only 6 relays per bit. First of all, let's have a look at the truth table for a full adder, because everything for the ALU derives from the full adder. There are patterns that develop, and if you have a look at our inputs A and B and our carry input to a bit, there are patterns that show up for the carry output and also the sum bit out. If A and B are equal, if we have 2 zeros or 2 ones, the carry in bit actually shows up as our sum out. And if A and B are not equal, if we have a 0 and a 1 or a 1 and a 0, that carry in bit actually shows up as our carry out bit, and our sum out is actually the inverse of the carry out. If you examine that truth table for a few minutes, you should be able to see that it'll be very easy to build a multiplexer to select the correct output bits for both C out and S out if we knew whether or not A and B were equal. Okay, we can extend this truth table and extend the functionality of our arithmetic and logic unit to include an XOR function in addition to an addition operation. And in this case, all we need to do is force our carry input to be 0 for each bit. And here we have carry input of 0, A and B being 0 gives us 0. Carry input 0 here, 0 and 1 gives us 1. Again, 1 and 0 gives us 1. And last but not least, 1 and 1 gives us a 0 for our output bit. We can also take our C out bit, and if we set our C in bit for each stage of our ALU to 0, and instead of taking our output and applying our S out to the data bus, if we apply C out, we'll actually generate an AND function. You can see here 2 zeros give us a 0, 0 and 1, or 1 and 0 also give us 0, and only in the case where we have 2 ones for A and B do we have a 1 for the C out. We can also generate an OR function by taking our output from C out instead of our sum bit out and setting our C in bit to 1 this time. So if we take the case where C in is 1, we'll have a 0 only if both A and B are 0, but if anything else is a 1, we will have a 1 at our output. This logic is actually sufficient to do just about any logic operation or arithmetic operation you'd want to do with an ALU. We can do AND or XOR and add and subtract. We can do a shift left by adding a number to itself. We can invert a number by XORing it with FFFF. We could also negate a number by subtracting it from 0. So this entire logic right here, this is all we need to build a fully functional ALU. Now the circuit design that I've come up with for this project is shown right here. This is as simple as I could get the logic. It has the advantage that it uses the fewest number of relays and switching contacts of a design that I've seen on the internet. It has the disadvantage that there is a mechanical ripple carry through number 4 relay right here. You could eliminate this mechanical ripple carry effect, but you would have to add another multiplexer there, so you'd go to 7 relays instead of 6. And as a proof of concept, this actually works fairly easily and simply. There is one relay on the input stage here. This relay just serves the purpose to optionally invert our data input, and that optionally inverted data input will get stored in either register A or register B up here. Once the data is stored in register A and B, the second half of our registers, which aren't used to actually store the data, generate an exclusive OR function. So if the data stored in A and B is the same, that will trip this multiplexer here, and we'll select the appropriate outputs for our data bus and our carry out outputs from our adder circuit. We also have on the front end here of our carry in flag, or our carry in bit, we have some logic which will, in combination with this signal here, logic bar, and our OR and OR bar, we can actually generate either a 0 carry in or a 1 carry in, or just let our carry in flow through for each stage. And on the output side, we have a multiplexer to select for our data out whether we want the sum bit or the carry bit. Okay, let's have a look at this circuit in action. And because this circuit is actually slightly more complex than some others that I've designed, I've put together an actual control panel for it. We have some data switches here which load data onto our data bus. Once the data is on the data bus, we can clear and set register B or register A to save those values into those registers. We can optionally invert the values before they're saved into those registers. We have also a carry input flag here, which controls the carry into the least significant bit. Over here we have our function select, adder function up top here, logic functions and or XOR on the bottom. We can select when we are in our logic mode whether we want an XOR or an AND OR output. And the last switch here, if it's in the center position, the outputs are not driven onto the data bus. If it's in the up position, that drives our OR output onto the data bus, and if it's in the down position, we'll drive our adder or our XOR and or our AND functions onto the data bus. Okay, let's turn things on here and we'll show you how this circuit looks. Here's the circuit. And in this circuit we have actually several LEDs. This red up here is our carry in to the least significant bit. And these other two reds are the least significant bit and most significant bit of our A register, least significant and most significant bits of our B register. And we have least significant and most significant bits on the data bus here, along with our carry output from the most significant bit. And one more LED which is not lit up right now is yellow guy in the corner here. That is the 0 flag, which indicates a 0 result on the data bus. So I can actually load some values into a register. We'll store a 0,1 into register A, and we'll store a 0,2 into register B, and now I'll be able to add 0,1 plus 0,2 will give us, in this case, 4, because we have a carry input over here, so if we turn that off, we'll get 1 plus 2 gives us 3. Okay, we can also demonstrate our logic functions. Logic, we'll select our logic mode. We'll do an exclusive OR, which if we do an exclusive OR, you'll notice our carry output bit is cleared, and we have a 1 and a 1 show up at our output. If I change my carry input, that does not affect my logical XOR. I can also perform an AND function. Here I have my AND function with a 0,1 and a 1,0 gives me a 0 output. And the last item I might show would be the OR function, which is 0,1 ORed with 1,0 gives me, of course, 1,1. And that is the 2-bit ALU implemented using only 12 relays.